Okay. So we found that the most critical, before the break, we found that the most critically loaded is element C. Okay. So now if we go to construct element C, okay, we are going to construct element C. I'm going to use this small space. We're going to construct the stress state of element C. Okay. So if we're going to view element C in this manner, that's our element C. And then if I were to sketch our transformation, this is our X. And then this is our Y. And then now our Z. Okay. So basically, I've rotated in such a sense that this is how our transformation look like. And we are aware that we are going to have a stress X compression, right? Because minus px over a minus mzy over izz is compression. Now the torsion, right, on element C, if we look at the torsion, the torque, this is torque in the x direction, right? So this is how the shear will behave. Okay, this is how the shear, and the other side there's also the other shear. Okay. So when that's the case, right, we are going to label this into points, okay, on our mole circle, right? So this will be our point X. So this is our point X surface. Over here will be our point Y. And the surface over here will be our point Z. Okay. So now we're going to construct mole circle now. Okay. So what we know is stress Y is equal to stress Z, and then equal to 0. Okay. And then we are going to sketch 3D mole circle, and I'm going to squeeze into here. Okay, before I go on, this is a sketch of element. What we are trying to do here down here is to see whether we're going to use the left hand side or the right hand side. Okay, the tau max is equal to sigma x over 2, or tau max equal to sigma max minus sigma mean divided by 2. Okay, so it all depends on the principal stresses. So again, this is just a sketch, right? So I'm going to focus on the negative. You know what? Since we are here already, I'm going to use a new page. I do apologize for squeezing it so much. Okay. So we're going to sketch mole circle. So over here, this is our normal stress, right? And over here, this is our shearing stress element rotate clockwise, element rotate anti-clockwise. Okay. So we are just going to use this transformation over here to sketch, okay, our mole circle. Okay. So we know that our stress Y and stress Z line are at the 0 line. Okay. So we also know that our point Y is over here, right? Because point Y has 0 normal stress and 0 shearing stress. Then we are going to have a normal stress X of stress X, and then we have our shear. So point X, okay, if we put a pin, sorry, if we yeah, point X, if we put a pin, okay, put our finger over this side, okay, the element will rotate in a clockwise manner, right? So whether clockwise or anti-clockwise at this stage is not so critical. More or less, we want to locate our stress X, point X, and point Z first. Okay. So that's our point X and point Z. We draw a straight line across, right? And then we draw our first circle. So this is our first circle. And then the other circle, okay, so we know that this is for our XZ plane. Okay, that is for our XZ plane. And then we have another circle over here. And this is for our YZ plane. And our last circle right? And this is for our XZ plane. Sorry, YZ plane. So after we have constructed our mole circle, right? So this is our stress A, right? Over here, this point over here is our stress B, right? So we can conclude from here, we have to apply, okay, based on 3D mole circle analysis. Okay, none of the principal stresses, i.e. stress A and stress B are equal to 0. Okay, so therefore, the formula we must apply is tau max is equal to half, right? Stress max minus stress mean divided by 2. Okay, or it can be half stress A minus stress B divided by 2. Or, sorry, for this case, it's stress B minus by stress A divided by 2. Okay. So that is the purpose of constructing 3D Mohs circle, is which one to use. Okay. So we confirm that this is the formula to use and not, right, tau max is equal to stress max divided by 2. Okay. Okay, so now after knowing this, we have to find, okay, from here, we have to determine stress max and stress mean. Okay. So let's look at, so our element, so I'm still going to copy our element. So we need to find what is our stress X value. Okay. So stress X due to axial load, which is our Px. So it's equal, okay, is equal to stress X is equal to Px. So Px is equal to, if we look at our question, is equal to 2,500. Okay, 2,500. And we have to put a negative sign, okay, minus 2,500. Over pi c squared, okay, where c is the radius of the shaft. Okay. Then we also have to find sigma x due to bending moment, which is your m, I think it's mz. Wait, let me look at, yeah, it's our mz. So this is equal to stress x, moment is equal to, we calculate the moment, what was it? It's equal to mz moment is 27600. Okay, m y is equal to c, and I, second moment of area, is pi over 4 t to the power 4. Okay, so this will be equal to 27600. Wait, 27600. 150 times 12. Wait, moment is, hold on, did I get my moment value? 1500. Oh, so sorry, it's 18,000. I do apologize. I used the wrong number. It's 18,000. So 18, 1, 2, 3 divided by times 4. It's 72,000 minus 72,000